Don't you dare ask me what optics has to do with medicine or biology or zoology or marine biology or any of the life sciences, because by this point it should be abundantly clear that the eyes of human beings and of all organisms are really just lens systems designed to capture the light and form images on the back of the eye, which is called the retina. So if you would go to the physics of the human eye slide, I will make this a little bit more clear. Without a doubt, the human eye is the most remarkable of all the optical devices. It is really remarkable because it actually adjusts the lens in our eyes. Like there's muscles in the eyes that squeeze the lens so that the focal length changes so that we could adjust where we're actually able to focus images. Okay? So the eyeball is approximately spherical with a diameter of 25 millimeters. Light enters the eye through a transparent membrane called the cornea, right? It's a kind of protective surface. The membrane covers a clear liquid region called the aqueous humor, behind which are the diaphragm, the iris, the lens, and a region filled with a jelly-like substance called the vitreous humor. And then finally, on the back of the eye, you have the retina. The retina is the light-sensitive part of the eye. So this is the part of the eye that actually senses the light falling upon it so that it can send signals to the brain indicating a certain image or colors or lights, right? In fact, neuroscientists actually consider the retina a part of the brain itself. Okay, so it consists of these rods and cones, which many of you probably know about rods and cones and how they, what role they play in forming images. When stimulated by light, these structures send electrical signals via the optic nerve to the brain, which interprets the image detected by the retina. All right, how complex is that? How unbelievably wild and beautiful is it that we have this structure that is able to focus light, change that focal length of the light, not only detect, shapes, but actually colors as well. I say it again and again, but the human body, animal bodies, which are able to do similar things, are absolutely amazing to me. Okay, so in this next slide where it says how the eye works like a lens, you can kind of see what's actually happening here. You can see beams of light leaving an object at a distance and actually forming an image on the retina after being bent, refracted by the lens inside at the front of the eye. Okay, that's the job of the eye, right? Your eye, without having studied physics at all, has figured out how to use refraction to form these images. And if that's not interesting enough, another application of optics and this concept of refraction to the world of biology and medicine especially for those of you who are interested in becoming an optometrist or an ophthalmologist. So we can use the power of refraction. We can use this idea of optics to transform bad eyesight, right? To create corrective lenses, right? And so there's two different types of bad eyesight, which you probably know. There's nearsightedness, which is also called myopia, okay? So a person who is nearsighted or myopic can focus on nearby objects but cannot see objects far away. For such a person, the far point of the eye is not at infinity and may even be as close to the eye as 3 or 4 meters, all right? So for a normal good set of eyes, it's like you could, pretty as an approximation, see light coming in from an infinite distance, right? But a nearsighted person, if they go beyond a meter or so, right, things start to get blurry. In other words, the image, where the image is formed is either in front of or behind the retina, okay? Meaning it's not a crisp image that's formed precisely on the retina. So in this case, you have a diverging lens that's designed to transform a distant object, okay, so an object that's very, very far away, into an image located at the far point. So that's the whole goal of a corrective lens for someone that's nearsighted. You want to create a lens that takes an object that would be at infinity and puts it at the spot where the person can actually see, which is called the far point. All right, let's see how this works. Let's do a problem. So finding the right lens for a myopic person. A nearsighted person has a far point located at about 521 centimeters from the eye. That's 5.21 meters. Assuming that eyeglasses are to be worn 2 centimeters in front of the eye, find the focal length needed for the diverging lens of the glasses so that the person can see a distant object. Remember, the goal of correcting nearsightedness is to take an object located at infinity and put the image at the far point of the patient. Okay? So how do we do that given our little thin lens equation? Okay? So the goal here, once again, the goal here is I have some object distance, and I have an image distance, and I have a focal length. Okay? Now, remember, the whole goal here is to take something that would have been at infinity, right? An object that would be at infinity, and you want to take that object and make its image be at the far point for this nearsighted person. This person's far-sighted point is 521 centimeters. So I'm going to put 521 there. And this is the point where you should be like, oh no, it's not actually 521 centimeters away from the corrective lens. The corrective lens is 2 centimeters away from the eye. So really, this should be 521 minus 2 centimeters. So that's actually going to be 519. Okay? So if we take a look at this, so here I have an eyeball, right? And I have an object, let's say, that's out here at infinity, right? But here's my far point, right? Here is, there's my corrective lenses. So I'm wearing glasses. I hope you guys can see what's going on there. So here's my object at infinity. You know, we'll say approximately infinity. And we want to, so this is my DO right here, right? This distance, all right? But I want the image formed by this lens to actually be right here, which is where the far point is. This is the far point. Not the fair point, but the far point. Okay. And this distance here is going to be the 519. Okay. Okay, Scott's still waking up today. All right, so I take something at an infinity, but I want this lens to form an image. Now, if this image is on the same side of the lens as the object, what kind of image is it? It's going to be a virtual image, okay? And we also know it's a virtual image because it's upright. Okay, we're not putting on the glasses and seeing the world flip upside down, right? So that means that this is going to be a negative 519, okay? So what focal length must I need to do that? Okay, well, 1 over infinity is actually just 0, right? So 1 over the focal length is going to equal 0 plus negative 1 over 519, right? This means that this goes away, and if I just take the reciprocal, the focal length is just going to be negative 519 centimeters. Okay? And the question asks, what does this minus sign mean? It means that for correcting nearsightedness, you need a diverging lens. Remember, negative focal lengths correspond with diverging lenses, and so you will have a diverging lens form an image here because the eye can't see this image way over here at infinity. It can't. So the lens has to take that object and put it to where the eye can actually see. And then the eye is like, oh, yeah, okay, now I can focus that. Okay? You see how that works? Super, super clever. Basically, when you're correcting nearsightedness, all you're doing is you're putting infinity in for the object distance and the far point for the person over here. Okay? So in the next video, we will discuss how to correct the vision of someone who is not nearsighted, but who is farsighted, also known as hyperopic.